In this study, we propose a deep reinforcement learning framework for UAV-UGV cooperative routing to efficiently visit a set of task points. The challenges lie in the vehicle's heterogeneous nature. UAV or drone is fast but fuel limited, while UGV is slower but can recharge drone mid-mission. Moreover, the drone's fuel consumption is stochastic, influenced by wind conditions. Our approach optimizes routing while minimizing mission failures due to fuel depletion with a proposed risk-aware policy. As the policy, we present an encoder-decoder transformer architecture. The encoder extracts feature embeddings from raw task points input, while the decoder selects actions sequentially based on the encoder's embeddings and the current state context. As the action, the drone can either visit a mission point or recharge via UGV. First, we define a risk function that represents the expected number of failures, using a failure indicator function to identify when the vehicle enters a failure state. Our objective is to develop a risk-aware policy that minimizes mission costs while ensuring that the risk stays below a specified threshold. Next, we define the probability distribution over trajectories based on the policy. To ensure risk awareness, the loss function includes both mission cost and a penalty term, where lambda balances minimizing cost and meeting the risk threshold. The optimal policy is then found by solving a min-max optimization, minimizing the loss with respect to policy parameters, while maximizing with respect to lambda to enforce the risk constraint. The policy is trained and tested on 3 problem-size distributions of task points. We use reinforce for the training algorithm. We compare our Ra-DRL policy's performance across risk thresholds and decoding strategies. While the sampling strategy provides better solution quality, it comes with higher risk. Stricter risk thresholds make the model more restrictive, increasing mission time. Compared to a risk-aware nearest neighbor baseline, our DRL policy consistently outperforms in both solution quality and risk control across all problem sizes. Our policy generalizes well to larger problem sizes as well, minimizing mission time while maintaining risk control. We deploy our policy in a gazebo simulation environment using the ClearPath Husky UGV and a PX4-based drone. The simulation integrates sensor data and control commands via Mavros for the drone and a SLAM-based navigation stack for the UGV. We have modeled vehicular characteristics like speed and stochastic fuel consumption for both the drone and UGV, with wind conditions integrated into the environment. The drone uses image processing for autonomous landing on UGV. For the policy with a risk threshold of 0.05, the drone takes a safer route, recharging 4 times to complete the mission in 12 minutes, with the fuel level dropping to a minimum of 22% of its total capacity. We have also tested a policy with a higher risk threshold of 0.1, where the drone takes riskier actions, completing the mission in 7 minutes with 2 recharges, but the fuel level drops to 11%. In conclusion, the proposed risk-aware DRL framework enhances UAV-UGV collaboration, balancing cost and risk, outperforming baseline by up to 60% and generalizing well to larger scenarios.